Okay. Good morning, everybody. Welcome to this new seminar from Instituto de Astrofísica Andalucía in Granada, in Spain. Today, we will have the talk by Dr. Jeffrey Hodgson from Sejong University in Korea, and he will talk about cosmological QUOKKAS. Jeff studied his undergraduate honors at the Curtin University in Perth, in Western Australia, working on intra-hours variable radio sources. This is now the International Center for Radio Astronomy Research. Then he did his PhD at the Max Planck in Bonn, in Germany, where he worked on mountains on the global millimeter BLBI array data. Then he moved to Korea Astronomy and Space Science Institute in South Korea, working on the Korean BLBI network data. Now he is assistant professor at the Sejong University in Seoul in Korea. And he's spending, I think, a week or 2 weeks here at the IAA in Granada. And you can find him at the IAA. Welcome, Jeffrey. Thank you very much for giving us this talk. And the floor is yours.
Yeah, thank you very much for the introduction. Yeah, very glad to be here. There's definitely worse places in the world to be than Granada, one of my favorite places. So today I'm going to talk about the project I've been working on for the past couple of years and starting to make some progress on recently, which is the Cosmological QUOKKAS project. So just sort of a brief outline of the talk. I'm going to give a brief history. So actually, this is a sort of an outreach talk or a shortened version of an outreach talk I gave a while ago, which itself was inspired by a talk I saw many years ago by Terence Tao, who's a Australian mathematician, actually. So I'll talk about that, and in general, I think it's pretty interesting for everyone. Then I'll introduce the QUOKKAS project, which stands for Cosmological Quasar Observations on the KVN from Korea to Australia and Spain, potentially with the Airbus. They'll describe the methods, some preliminary results, and then introduce the array that we are just about to start doing regular observations using. All right, so let's start with a bit of history. So basically, the QUOKKAS project is all about measuring distances, which might sound boring, but is actually very interesting because Hubble, of course, discovered the expansion of the universe by doing this, and the Hubble Space Telescope is named after him for this reason. One of the key science projects of the Hubble Space Telescope was to measure the cepheid variables in the distance ladder. But the funny thing about distances is that they're actually one of the most difficult things to get in astronomy, and that's kind of funny because they're actually one of the most important things you need to get in astronomy, because if you don't know how far away something is, it's very difficult to work out what's actually going on inside the source. So basically, this is sort of a subtle point, which I think even professional astronomers sometimes forget about, which is that the more redshifted something is, the further away it is. This is quite a common thing that people hear, even non-astronomers might well know or would have heard something like this. But this is only really sort of true. So it's only true if you assume that there is in fact a relationship between the redshift and the distance. And we do make that assumption. So in some sense, we can say, the more redshifted something is, the further away it is. But this is only because we've measured and found a relationship between the distance and the redshift of a source. Okay, so how did we actually get here? And so the story of how we got here goes back, I'd argue, thousands of years. So basically what we have is called the distance ladder. And on each rung of the ladder, we sort of build on the previous rung of the ladder. And the first rung of the ladder is in fact the size of the Earth. And what surprises many people is that even the ancient Greeks knew this surprisingly accurately, like to within about 5% or so, which is not bad for over 2,000 years ago. So how did the Greeks know that the size of the radius of the Earth? Well, they knew that the Earth was spherical for a start. So some obvious points, like they saw that ships would just sort of go quote unquote down over the horizon. So they knew it wasn't flat, for example, despite what many people on the internet might try to convince you of. But they also knew that the boundary of the Earth's shadow during a lunar eclipse was always circular, and a disk would make elliptical shadows. So this is a subtle point which actually becomes important later. But even Aristotle knew this, over 2,000 years ago. But actually, it was Eratosthenes, around 200 BC. He used the differences in the shadows and the distance between the locations to determine the size of Earth. So he knew that there was a special well, like a water well, in a place called Cyane. And at certain times of the year, it basically would not have a shadow. And so he knew that the Earth was a sphere, or roughly spherical anyway. He knew that in Alexandria, that at the same time of the year, that the shadow of a column would have an angle. So using some basic trigonometry, he was able to determine the size of the Earth, and the value he got was about 6,800 kilometers, which is pretty impressive given compared to the modern value of about 6,377 kilometers. And you got to remember, back then they didn't even have an accurate value of pi. So I think that's all the more amazing that we could they could actually do this. Now, the thing is, once you know the size of the Earth, you can actually do a lot more things. So that brings us to the second rung on the ladder. So it turns out that by knowing the size of the Earth, it also allows us to measure the distance to the moon, which might not seem obvious, but it was actually Aristarchus who did this way back in the day, once again, like 2,000 years ago or so. So lunar eclipses are due to the shadow of the Earth on the moon, which is roughly speaking, an Earth diameter in size. And we know that because during a solar eclipse, the moon basically almost exactly covers the disk of the sun on the sky. So we knew that, and we knew that the lunar eclipse takes about 3 hours. And we knew that the moon takes 28 days to orbit the Earth, basically a month. That's where the word month comes from in basically every language. We basically doing some geometry, which in fact on the right here, you can see the original drawings from this. Basically with these bits of information, they worked out that the moon must be about 60 Earth radii away. And because we knew the radius of the Earth, we basically said 60 times 6,800, and we got about 410,000 kilometers. The true value today is about 384,000 kilometers. So I think personally that is incredibly impressive that they could work out the distance to the moon with 6% precision. Sorry, I shouldn't say accurate, I should say probably precise, to 6% even 2,000 years ago. So that's pretty cool. But then this is where the problems started to come up for the ancient Greeks, was trying to work out the distance to the sun. And it turns out getting the distance to the sun is really one of the most important measurements in all of astronomy. In fact, it's so important that we actually call it the astronomical unit. So that I think gives you an idea of how important distances are, and indeed specifically this distance. And you'll see why that becomes important later. And I suspect a lot of you can already guess. So basically, with the distance of the sun, so Aristarchus also tried to estimate the distance of the sun, and the way he did it was he was measuring the angle between the sun and the moon at the first and last quarters. So you can sort of see the little diagram here. So it's like, okay, there's a slight angle in the third and the first quarters, because he knew that basically the quarters were due to the shadow caused from the sun. And he knew this was about 3 degrees. But because we know the distance of the moon, we could solve for the distance to the sun, basically. But the problem was they couldn't actually make these measurements particularly accurately. So due to the inadequate data of the time, he thought that the sun was about 20 times the Earth to moon distance, when in fact the true distance is closer to 400 times. But one of the interesting things was that Aristarchus basically used this knowledge to predict the heliocentric model of the solar system, and he came up with it about 1,700 years before Copernicus. And interestingly, so as we'll talk about on the next rung of the ladder, in fact, it was because of the inadequate data is what, in a sense, led to the Earth-centric solar system model for being so popular for such a long time. And so we'll talk about that in a second. So, with the distance to the sun, the estimates were greatly improved in the 17th century by Copernicus, and then by Brahe and Kepler. Kepler got the distance to Mars in a very clever way. So actually, I kind of like this. The way that the Kepler got the distance to Mars is really cool. So he knew so basically, in order to triangulate a distance, you need to have a fixed point. And of course, the Earth and Mars are moving at the same time. So what Kepler did was he waited 1 year, one Mars year, for Mars to come back to the same point. So then that way, in effect, it would be a fixed point because it was 1 year later, but the Earth would have moved in that time. So you had a fixed point of Mars and then 2 data points for the Earth. And with this, he was able to then calculate the distance to Mars, and then therefore the distance to the other planets, and of course the sun. And even Einstein said this was a stroke of absolute genius from Kepler to do this. These days we use radar, for example, so we can use planetary radar to get the distance to, for example, Venus, and we can get we can use Kepler's laws to get a lot of these distances extremely accurately. So these days, the value of an astronomical unit is 149,597,870.7 kilometers. So we could talk a lot more about this. It's a very interesting topic in and of itself, but I have to just briefly mention it. Okay, so once you know the distance to the sun, we can then use parallax to measure distances to objects outside of the solar system. So I'm fairly confident everyone attending this talk would be familiar with parallax. But basically, in case just a quick rundown on it, it's very simple. So it's basically the same idea as how our eyes do depth perception. So we observe a nearby star compared to distant stars, and then at a 6-month intervals, we will measure the apparent shift of the the star compared to the background stars every 6 months. By measuring that shift and combining with the astronomical unit and some trigonometry, we can then get the distance. So interestingly, that the ancient Greeks didn't see parallax was interpreted as the stars being impossibly far away. And that actually is why that led to the Earth-centered systems of the solar system. Models of the solar system, I should say. So, because even the Greeks expected to see parallax, they just couldn't see it. And so they thought that meant that the stars must be impossibly far away. So that doesn't make any sense. And the reality turned out to be that actually the stars really were just that far away. It's just they couldn't imagine things being really that far away. So that's kind of a funny thing to remember when we're looking at some of the discrepancies in our data today, I think. I'm going quick sort of side tangent onto standard candles before I go up to the next rung, and you'll see why. So basically, at some point we can't resolve the motion of the stars using parallax. But if we know how bright something actually is, we can measure how bright something appears to be, and then we can find out how away it is pretty simply. And this is known as a standard candle. And in quite in a similar way, if we know how big something is, we can determine how far away it is by measuring how big it appears to be. And this is often called a standard ruler or standard rod. So these are, I'll come back to these in some time, but just keep them in your mind when we're talking, when we go to the next few slides. So once we had good parallax distances to the nearby stars, we could also use our telescopes to measure the colors of stars. And because of the black body radiation, if you know the color of the stars, you can get things like its luminosity and its temperature and things like this. As I said, distances are really important, because once you know the distance, you can determine a lot of the actual astrophysics of the sources that you're looking at. So when you have the colors of the stars, so we had to develop telescopes by this point, and we can measure distances to stars using parallax. And some astronomers were trying to do this for as many stars as they could possibly see. And because we knew the distance, we could find out how bright they actually were. So basically your luminosity. When they did this, what they found was there was a relationship between the color of the star and their actual brightness. So this is a whole big science in and of itself. But the important thing for our knowledge today is that if you measured the color, you could also get a distance, basically. And so in a way, this is a kind of standard candle. And so you might know the astronomers who came up with this. This is Hertzsprung and Russell. So, and then on the right here is, of course, the very famous Hertzsprung-Russell diagram. And so, as I said, like this, stellar astrophysics and stuff, there's a whole, institutes are dedicated to this. But for our purposes, basically what you need to know is that because of parallax, we were able to get distances and find out this relationship. And that meant that relatively easily you could measure the color and its brightness, and you could combine that to get an estimate, at least, of the distance, albeit not as accurately as parallax. Okay, so then the next rung up are a special kind of star, which is called cepheid variables, and these are actually the stars that made Hubble famous. So basically, cepheid variables are very bright stars that pulsate in a very predictable way. So basically, the brighter they are, the longer the pulsations take, something like that. So that what that meant was that by measuring their brightness and period, their distances could be determined. But of course, you've got to remember that this relationship itself is calibrated on cepheids that are close enough to be measured via parallax or via the color and luminosity and brightness relationships, these sorts of things. So Hubble and others used this to measure distances, and because they were bright enough to be able to be seen in other galaxies. He was able to, and this is in fact the original plot over here from Hubble, and he found that the galaxies further away appeared to be redder than they should be. And this is really the discovery of the relationship between redshift and distance. So he had discovered that the universe was expanding. So actually, I should probably rephrase what I put right there. It's not really that he discovered that the universe was expanding. It's more that he interpreted the redshift as due to the expansion of the universe, I think, is a more accurate way to say that. So nevertheless, calibrating these cepheid variables is very important. And so Hubble found that the universe was expanding, but he determined that the rate of expansion was very, very high, something like 500 kilometers per second per megaparsec. And this was due to the bad calibration of the cepheids. So in fact, one of the, as I mentioned at the start, one of the major goals of the Hubble Space Telescope, which is probably the most famous telescope in the world, was to in fact calibrate the cepheids and measure their distances better. And it turns out this becomes important even today and very, very soon. So as I said, so Hubble found a relationship between the distance and the redshift. And this was predicted by Lemaitre. So the result is known as the Hubble-Lemaitre law. And the expansion rate of the universe is governed by the Hubble constant, which is colloquially known as H0. And as I said before, this is interpreted as expansion of space or space-time itself, and is these days taken as evidence of the Big Bang model of the universe. And because of this itself led to the prediction of the leftover glow from the Big Bang, which of course is the cosmic microwave background. So the cosmic microwave background, of course, I'm sure everyone here is familiar with it. The CMB is a huge science, hundreds or thousands of PhDs have been done on it in and of itself. But for our purposes, the important thing to know is that it's at a redshift of about 1,100. And using some model is a bit model dependent, but basically by observing the cosmic microwave background, we can indirectly infer a measurement of the Hubble constant. And at the moment, if we do that, the measurement of the Hubble constant using the CMB is about 68 plus or minus 0.5 kilometers per second per megaparsec. And the very interesting thing is that if you do this using the distance ladder that we spoke about before, you get a value of about 74 plus or minus plus 1.5 or so, which translates to something like about a 4 sigma tension at this stage. So so the big question about this is whether or not this tension is real. So is it that if you measure the Hubble constant at high redshift and low redshift, you actually get different answers? And if that's the case, that would be very interesting because that would be suggesting new physics. Or is it systematics in our observational data? So a lot of people are working on this problem, including myself. And nevertheless, we will come back. We'll come back to that. Just know that it's one of the big questions in astrophysics today. But for now, let's go on to the next rung. And the next rung, of course, is the famous supernovae and dark energy. So supernovae themselves are amongst the brightest objects in the universe. They can be seen clear across the universe, which is pretty amazing. I always like the thought that supernovas are so crazy that you actually get irradiated by neutrinos. But that's just how much energy is released in a supernova, which is pretty crazy. Anyway, there's a special kind of supernova called the Type 1a. So it's very famous, which explodes in a sort of unique way, which means that there's sort of somehow a standard explosion of sorts. Basically, their relationship can be calibrated on galaxies where the distances are known via the cepheids, which are themselves calibrated on the colors of stars and parallax measurements. So you can see this is really a ladder that you're working up to get these distances. So the problem with the Type 1a supernova is that you can't actually get the absolute distance. It's only a relative distance. So you really do need the calibration with the lower rungs on the ladder here. So in a sense, what the supernovae can measure is the curvature of the distance redshift relationship, while stuff like cepheids can measure your up or down, then that's your Hubble constant. So basically, you can think that your Hubble constant is moving you up or down on this graph, while the curvature here is what they call omega m, and that's the matter content of the universe, at least under the Lambda CDM model. But I'm getting a bit ahead of myself. The important thing for people to know is that basically back in the 90s, they started measuring the distances to these Type 1a supernovae, and what they found was that when they went to higher and higher redshifts, basically the supernova appeared to be fainter than they expected. And this was interpreted as the accelerating expansion of the universe, and what is commonly referred to as dark energy. Although I don't really like the term dark energy, because I think it's already interpreting it a bit more than it really is, because it's not really clear that it's energy at all, let alone dark. But one thing to keep in mind is that there are a lot of people starting to cast doubt on some of these results. So, for example, Professor Lee at Yonsei University in Seoul is sort of claiming that basically the dark energy signal can be removed if by evolution in the Type 1a supernovas themselves. So, I mean, I'm not an expert in this, but nevertheless, there are definitely people starting to poke around at the edges. Either way, I think you can probably see that there is a big need for independent distance measurements, so that we can try. So at the moment, you really only have the Type 1a's at high redshift. So an independent check on all these sorts of results is very important. So you can probably see where I'm going with this. So going into the future, so basically, we want ever further distances, ever further redshifts. As I said before, the Hubble constant is itself still a source of big controversy. So while we know that the universe is accelerating its expansion, at least if you trust the Type 1a's, we still don't know. We have no idea why or what causes it. And I think the really cool thing is that we, in effect, know all of this because we know the distance between the Earth and the Sun. And that in itself is a story that goes back thousands of years. I think that's really cool. And I think it's cool to sort of think that, even as a modern astronomer, we are really continuing a scientific process that stretches back thousands of years. So I think that's pretty cool. And you should remember that when you're fighting LaTeX or something and like getting frustrated. Okay, so this all leads into like a bit more astrophysics-y sort of a slide. So some of the open questions we have. Of course, I've spoken about the the Hubble constant controversy, and why we need new distance measures. But fundamentally, we don't know what 95% of the universe is. So we have our lambda CDM models, and today we think we got like something like 65% or so, or 70% dark energy with 25% dark matter. We don't even know what dark matter is, or even if it is matter. A lot of things we don't know, and it's really only the 5% baryonic matter in the universe that we have some handle on, and even then, there's a lot of problems inside that data. Of course, what's the question? Like at redshift equals 6, we want to know was really the dark energy component only 1%? Was dark matter 82%? These is what people sort of predict, but at this stage we don't have any direct sort of checks on that sort of thing. Maybe dark energy, or is which is often interpreted as the cosmological constant. Maybe that's not. There have been some people claiming that that's a time variable thing. Short answer is we just don't know. And really, I think this is going to be one of the most fruitful areas to be looking for real big breakthroughs in our understanding of the universe. So as I said before, so was there really so little dark energy in the early universe? Our models say yes, but only one way to find out. So Zhao et al. In 2017 had hints of time evolution and dark energy. And Causality et al. Also published in Nature Astronomy, claiming some deviations at high redshift, actually using AGN, but in a very different way. But the key point here is that any variations from the concordance lambda CDM cosmology would be expected to be seen at high redshift. So the current cutting edge, so of course we've got the type 1a supernova, which I spoke about before. These are the very bright standard explosions, and this has led to the sort of dark energy discovery and the Nobel Prize in 2011, and they can be seen out to about redshift 2, something like this. Also, we've got the baryonic acoustic oscillations, which are basically the imprints of the early universe physics on the large-scale structures of the universe. They have their own issues, but they can be seen out to a redshift of about 2.5 or so. But they sort of depend on the supernova measurements themselves, actually. So they're very interesting in their own right, but a little bit imperfect. So then, of course, the CMB, which we spoke about before. So basically, you're fitting your cosmological model parameters to the observed CMB power spectrum, and that can give you your cosmological parameters under the lambda CDM model. But of course, the big question at the high redshift it really is: does the distance redshift relationship trend continue as expected past roughly redshift 2 or so? That's the key question at the high redshift, as the Hubble constant controversy at the low redshift. So, active galactic nuclei as standard candles. So AGN are supermassive black holes, and at the center of massive galaxies that produce jets that move near the speed of light. When the jet is pointing towards us, we call them quasars and blazars, depending on the viewing angle. And they are the most continuously bright objects in the universe. So for obvious reasons, they've long been desired as a standard candle or a standard ruler. And so people have done reverberation mapping, which is very accurate, but it's very difficult to do. So they've done that on a few sources and got some pretty accurate distances. Using size scales, Gurvitz et al. In 1995 tried this. It's complicated, but has other dependencies. But there's actually, I should have updated this slide. There's a group in China who is working on this, and they seem to be actually having a little bit of success, which is very interesting. And then there's sort of parsec scale structures. People looked at this, and it seems to be not really possible due to complicated astrophysical reasons. So basically, many people have proposed that none have succeeded. So we need better methods. And of course, so this is a picture of M87, and I'm sure most people here are now very familiar with that particular image. So just a quick talk about this Rosaletti et al. That was in Nature Astronomy, and they used the UV X-ray luminosity relationship, which here is the log of the X-ray luminosity is equal to some sort of empirical relationship between the UV luminosity and some beta parameter, which has to be calibrated itself off the type 1As. They are claiming a 4 sigma deviation away from lambda CDM at high Z. I'm not sure that everyone really believes this, but time will tell. But they interpreted this as due to dynamical dark energy. So, so maybe some hints in the data here, and I guess we'll see over the next few years, so that we look at that. Okay, so that's where I come in with the Cosmological QUOKKAS project, which is I'm very proud of my forced acronym here. Stands for Cosmological Quasar Observations on the KVN from Korea to Australia and Spain. So it's cool because I've got 2 nested acronyms in there. So you've got KVN, which stands for Korean VLBI Network, and that itself contains VLBI, which stands for Very Long Baseline Interferometry. And of course, Korea is in there twice. So anyway, basically the project aims to measure distances to the active nuclei of quasars and blazars, basically. So how are we going to do it? Well, basically we're using the variability of AGN to our advantage. So the big problem with using active galactic nuclei is that they're very, very variable. So it's really hard to know whether or not they're really, bright and variable and close, and far away, or if they're close by, and but just not that bright. So it's very hard to distinguish between these 2 scenarios because they're all over the place and they do all sorts of crazy things. So basically we make one key assumption. That the variability that we are seen in AGN, at least at radio wavelengths, is reasonably constrained by the speed of light. That's the big assumption we're making. So basically, if we make that assumption, we have a sort of causality limited variability size, which is limited by your variability size is roughly the speed of light times the variability timescale. So the variability timescale, very loosely speaking, is the time it takes from the beginning of a flare to the finishing of a flare. And if you think that that is constrained by the speed of light, you can basically times it by the speed by c, and that'll give you at least an estimate of the linear size or the true size of an emitting region. So basically, you can think of it as measured in meters or kilometers or whatever you like. But then what we do is we measure the apparent size or the angular size on the sky using VLBI. And then you basically, that's it. Basically, you just say, okay, we could get the apparent size. We got the standardized, kind of like a standardizable rod of sorts, using the speed of light to calibrate it. And then you just divide the 2 with some 1 plus z corrections. And if you know the Doppler factor, which is a big problem, if you know the Doppler factor, you can get the distance to the source. So it's very, very simple way of doing these things. And in fact, it has been thought about before. There was a paper from some of the Finnish group in almost 20 years ago now, that did this, and they claimed to be able to detect the cosmology. But for some reason that's had like only 2 or 3 citations, so it seemed to have been forgotten, even by me. So I found out about it fairly recently. Anyway, so if we can get this to work, it'd be really, really cool, because arguably doing it this way is better than using type 1a supernova. I had to put a disclaimer in here saying the type 1As are awesome, because if cosmologists see that, they might get very angry. So the cool thing about it is that, at least in principle, we can constrain the Hubble constant and the omega m. So we can get both of them in one go. So it's sort of like a single rung method of getting distances. So we've actually tried to test our methods using the archival Boston University 7mm VLBA data. And so the thing is, like, our method is somehow geometric. So long as we can detect the source and resolve the source, we can, at least in principle, get the distance. So we published a paper about a year and a half ago now on 3C84, a very famous nearby radio galaxy, and I'll present that here. I should also point out there is also another assumption that we made here, and this will become important later. So in practice, especially for VLBI people, what you're actually doing to measure the size of an image, of the apparent size in a VLBI map, is you usually fit a Gaussian onto your data using diffmap usually. And then, but this is just a Gaussian. So if you want to convert that to the full width half maximum of the Gaussian itself into something more physical, if it's a disk-like geometry, we timed it by a factor of 1.6. And if it's a spherical geometry, we timed it by a factor of 1.8. In the paper, actually, we just put it in the middle and said 1.7 and included it in our error bars. So there's a paper from Lobanov et al., which talks a bit about this. But let's keep that in mind for now. So nevertheless, we got a distance to 3C84. So it's a redshift of 0.0178, and it's often compared with M87, so a lot of people will be familiar with it. So it's also a bit a low luminosity AGN, so it's we made an assumption of Doppler factor being 1. It's probably fine in a source like 3C84, at least in this context, was just a proof of concept. We got lucky. We saw a big flare with a clearly resolved component, and the distance to the source, the luminosity distance, assuming h0 equals 70 and 0.3 omega m is about 78 megaparsecs. Also, interestingly, there was a type 1a supernova measured in the source, and they derived a distance of 64 megaparsecs or so. So we can sort of directly compare against that. So this is the actual flare. So you can sort of see here in this sort of sequence of VLBI maps. So you can see it got bright. We had this component here, and so basically we went along. We just put a Gaussian on there. So we got the flux density and size as a function of time. It's pretty simple. This is just the archival BU data, so you can download it and have a look at it yourself if you want to analyze it independently and verify our measurements. That would be fine with me. Nevertheless, if you do that, this is what the light curve looks like. So we just fit basically the e-folding timescale to get the variability timescale, which is just 1 on the gradient of the log of the flux densities like this. And we got a variability timescale of 146 plus or minus 5 days. And then the size we measured was, from memory, 0.2 milliarcseconds or so. And you combine that under the Doppler factor being 1 assumption, and we get a angular diameter distance of 72 plus or minus 5 or 6 or so megaparsecs. So that's pretty cool. And this leads to a Hubble estimate of the Hubble constant at this redshift of 73 plus or minus 6 kilometers per second per megaparsec or so. But you really shouldn't believe this at this stage. So there are many. So it's pretty cool that we can do it, and that it seems to be roughly in the right area. I think is very promising, but I really don't want to overclaim any results here. Just to say that basically I'm confident that it more or less works, but maybe in the near future we can make a more strong claim about that, and we'll talk about that later. So basically that puts us somewhere like this in terms of the measurements of the Hubble constant. So we're going to have to do a bit more work to get the error bars down, and I'll talk a bit about that because systematics, of course, are going to be very important. Time. Oh, going out of time. I should point out that there's also another, we do have other radio galaxies like 3C111, where we can do the same trick. And also under the Doppler factor equals 1 assumption, more or less, we get consistent results. So we're still working on that. But I'll skip ahead. Okay, so we'll talk a little bit about the systematics. So we've got the observational systematics. So basically, the archival data means limited cadence in effect, which means that we not necessarily accurately determining the variability timescale. The source size might be smaller than the resolution of the instrument, but this is not such a big problem because we can assume a cosmology and sort of estimate how big the size should be. So we can just only measure flares that are sort of sensitive to our resolution of the array, something like that. A bigger problem is that the flares themselves can be quite messy, so it can be difficult to determine when a flare starts and ends. So actually determining the systematics of actually measuring the variability timescales, and this will be critically important. It's probably a PhD project in and of itself. So just to know that we are thinking about that, and this will be very important in terms of, especially if we see anything interesting, especially at the high redshifts. With the QUOKKA array, actually, it has limited UV coverage. I'll talk more about that. But actually, this has been looked at a little bit indirectly by Yanis Liadakis, but it seems we're probably okay. But really, we have to look at this in a lot more detail. So we've got sort of methodological systematics. So basically, stuff like how valid is the causality assumption. So one way to test this is to test the method on microquasars with known parallax distances. And also what is the exact geometry of the system? So there's a disk-like or sphere-like. So in principle, if we look at it with very careful analysis of the VLBI data, we can work this out. And is there any redshift dependencies on things like the critical angle assumption? So you can see here, we've got this these VLBI observations of Cygnus X3 actually, and you can see even in the visibilities that you can see the variability timescale. So, but trouble is Cygnus X3, the distance is not known so accurately. There's no parallax distance to there. So basically, as I said before, we're trying to measure two main model parameters, which are the Hubble constant and omega m. So H0 is sensitive to source space systematics and Z-based systematics. So basically the C delta T assumption and stuff like this. So that's the Hubble constant is more sensitive to that sort of systematic, whilst omega m is only sensitive to redshift dependent systematics. So long as there's no redshift dependent systematics, in principle, we can measure omega m relatively directly, and then the source space systematics will just add some scatter. So we can, in principle, get omega m and just observe lots of sources and lots of flares, basically, and average our errors down. So as I said, so for redshift dependent systematics, the core logic of the method may have source space systematics. So that's like your C delta T assumption, these sorts of things. But these should be free of redshift based systematics. So basically, you wouldn't expect that the speed of light assumption would vary as a function of redshift. It might be that it's a bit lower or something like this, but it would be pretty surprising, I think, if it turned out there was a redshift dependency in that sort of systematic. The Doppler factors, though, definitely can have systematics, but the important thing here is that they don't have redshift dependent systematics. So the solution that we're proposing here is that we use two or more independent methods of getting the Doppler factor, and then we look at the residuals, basically the difference between the Doppler factor estimates, and if they don't evolve with redshift, then assuming that these Doppler factor estimates themselves are not evolving in the same way, then that means that you're probably being dominated by statistical errors, which means that we can get around we can lower our error bars just by observing more sources and more flares, basically. So Blazars are what we see at the higher redshift. So as many people would know, they often exhibit relativistic effects like superluminal motions, time dilation, that sort of thing. And we need to get the Doppler factor, which is a function of the viewing angle to the source and the Lorentz factor. So in blazars, we can't just ignore the Doppler factor like we did in 384, but this is notoriously difficult to get. So I'm running a little bit late, so I'm going to skip ahead a little bit here. Basically, there's 3 different ways we can get it in a cosmology independent way. Got the equipetition Doppler factor, the jet speeds Doppler factor, and inverse Compton Doppler factor. So I'm going to skip ahead a little bit here. You can come and annoy me later, just to know that basically we do have some ways of doing this. I quickly looked at this on some archival data. And in fact, so here on the right, this is what a redshift-dependent systematic would look like. So at least we can do a check for these sorts of things, but you really shouldn't believe these plots. It's just very, very rough analysis here. Right, so the causality assumptions is something we've been working on a bit lately. So it's been indirectly looked at by Yanis Liadakis, who tried to find the best method for finding the Doppler factor in the blazar population. They found that the variability Doppler factor fits the population the best. And since the variability Doppler factor relies on the causality assumption, we think that it holds to within roughly the 10% errors of the experiment. Of course, on a physical level, the emission from 384 is due to synchrotron emission, which is itself, electrons being accelerated around magnetic fields traveling at nearly the speed of light. So given the physics of this, we think it's likely that the emission is tightly constrained, but maybe not exactly. And so as I said before, for the statistical errors, we can average down the errors by observing multiple flares within the same source. So that's a real good thing about this method. So we tried to calibrate some of our systematics on microquasars. So if we make the assumption that the causality arguments and the geometry, like disk or spherical light of a microquasar, are similar, or at least similar enough to a real quasar, we can calibrate our systematics on microquasars with parallax distances. So we can sort of mix together our systematic uncertainties here into sort of a fudge factor, which I call the K factor. I should say that this work has been done by my student Daehyun Kim. I've done some good work here, and we used Cygnus X1 for this, which has parallax distance measurements of 2.2 kiloparsecs, and we have the data here on the right, which comes courtesy of James Miller Jones in Perth, actually. And then we actually used the same VLBI measurements that were used for the parallax measurements to do the variability distance measurements. So very, very briefly, so we then calculated the K factor. So we had a size of roughly 2 milliarc seconds. dt was about 0.036 days, about 50 minutes. If we assume delta equals 1, we get a distance of 2 kiloparsecs or so, which means that the Doppler factor is probably about 1.1 in the source. If we put all this together, and this is very, very preliminary, I really have to stress this. So we need to work out error bars and all sorts of things. But basically, the K factor seems to be about 0.64, which means that 0.64 times the 1.8 times scaling, which is in effect measuring the speed of light on the source, gives a value of 1.15, which is 15% above the speed of light and actually above the experimental errors of 5 to 10%. So I'm interpreting that as meaning that we can rule out a spherical geometry in the source, which I think is quite interesting in and of itself. So that means that if you use the 1.6 times scaling for a disk-like geometry, comes out about 1.02. So that means that we agree easily within the observational errors with, so the C delta T assumption seems to be 1 in the case of in the case of a microquasar within our observational errors, which we're still working out. So it seems to suggest that there's a disk-like geometry, at least in the microquasar, and that the causality arguments agree within errors. As I said, so we're still working out on errors on this. So probably in the next few weeks, hopefully we'll have a more statistically based answer on this. I can give you some sigmas and things like this. So, but still, I think it's cool. So what's the implications of this for the Hubble constant controversy? Well, if these results hold up, we need to revise down the distance to 3C84 by about 6%, which actually means that our H0 estimate would be revised up by about 6%. But also remember that we made the delta Doppler factor equals 1 assumption. So if there is a mild Doppler factor in the source, this would increase the distance again, which would therefore lower the H0 measurement. So there's a bit of what's the word, degeneracy there. But basically, the way things are going out, so we'd probably need something like a Doppler factor of greater than 1.15 to match the observations with the CMB measurements, which actually I think is unlikely in this particular case, but we really need to confirm that and work out the error bars and these sorts of things. But basically, if we can independently work out the Doppler factor, and if it happens to be less than about 1.1, this would actually mean that we agree with the distance ladder, and that maybe implies that the tension is real. But this is very, very preliminary, and we're still calculating the error bars and these sorts of things. So, of course, we want to observe more sources and things like this and average down our systematic errors as well. But I'm just going to put that out there because it's informal talk somehow, and I think I think it's good to talk about these things. I'm not being too secretive or anything like that. And in this context, this is where the Cosmological QUOKKAS project comes in. So basically, in order to do this, we need to have high cadence and high resolution. By the way, a quokka is a small marsupial on an island off the coast of Perth, where I'm from. So basically, we're setting up an array between the KVN and MOPRA, and potentially with Yebes and even Italy. That gives us roughly an 8,000 kilometer baseline with observations every 2 to 3 weeks. We have an initial sample of about 20 sources or so, and this actually gives us really high resolution of roughly 50 micro arc seconds at about 3 millimeters. Also gives us a unique north-south baseline. We've already put a Mark 6 recorder and Octad backend down there. We've done test observations at 22, 43, and 86, and everything seems to be working. So full observations should be starting this year. Also, as a side note here, side quest, we tried to detect M87 and Sene at 3 millimeters and actually failed just recently. So that's a bit sad. I'm really running out of time, so I'm going to skip ahead. So this is the sort of simulated UV coverage for the QUOKKAS array. So basically for high cadence observations, so we use MOPRA for low declination sources, and maybe we can use Yebes for high declination sources. And yeah, so another thing, so MOPRA might be coming to the EAVN or the GMVA in the near future, which would be very cool for lots of things. I'm going to skip ahead because I'm running out of time. So basically, yes, we can resolve the sources using the archival data. I can recover the cosmology, basically, albeit with not many sources, because Mojave doesn't really have the resolution. But in principle, everything seems to work out. Okay, cool. So I'll read my conclusions here. So basically, we've demonstrated a new method for measuring distances to not just AGN, to cosmological objects. We tested some famous sources, and we found that basically they're consistent with other methods. There might be hints in the data that we might be more consistent with the distance data than the CMB. And so we're starting the Cosmological QUOKKA project to sort of quote unquote do this properly and hopefully sort out our systematics. So we can use a single method from low redshift all the way out to redshift 6 or so, at least in principle. So there's potentially thousands of sources here, so we can average down our errors. And of course, we can continuously monitor sources as well. So we can, in both ways, we can average down our statistical errors. We think that we've developed ways of handling the systematic uncertainties. So multiple Doppler factor tests will allow us to handle redshift-dependent systematics, or at least check if they exist. And low redshift sources can be calibrated on microquasars with parallax measurements. So basically, we think that if with a properly designed experiment, we can significantly improve our errors and hopefully start to answer some of the big questions in astronomy and in physics generally. So thanks. I think we're running a little bit late, but yeah. Cool.
Okay, thank you very much, Jeff, for this wonderful talk. And now the talk is open for questions. Please, for doing that, raise your hand pressing the reaction button, and then we can have the questions. Okay, we have one by Ioannis. Please go on.
Yes, hi Jeff. Thank you very much for the very nice talk. Nice to see you again also. So my question is, if I understand correctly, the methodology, you need to resolve the components that are flaring within a jet. Is this correct?
That's right, yeah.
Yeah. So I have two small questions. The first one is, do you need to fully resolve the component or marginally resolve it? Is it enough first? And the second is, how many sources would we actually have that the components within the jet can be resolved to apply the methodology?
The first, regard to marginally resolved, I think that's going to ultimately depend a bit on the SNR of so basically how bright the flare happens to be. So the brighter it is, I think the more marginal we can make our size measurements in effect. So it'll depend very much on the exact source. But in terms of the resolvability of the components themselves, it ultimately depends on the variability timescale of the component. So and that can be extremely variable. So just looking at the off-array data, there's like several orders of magnitude difference between the shortest flares and the longest flares. But luckily, it seems that, so these were the last slides that I skipped over here, but basically it looks like these longer flares seem to be what we're detecting in the VLBI. So we can sort of flip the logic a little bit and say, okay, on the QUOKKAS array, for example, say, okay, at this redshift, we are sensitive to flares of this length. And then we just sort of wait for and hope that a flare comes along that we can do the measurement on. That's basically the plan. In terms of how many sources, in principle, lots. Like it's a function of sensitivity and an observing time. So yeah, I don't have a good answer for that just yet, but we're starting with about 20 sources. But if we have some success, I think maybe we can easily expand out to to hundreds or thousands of sources, at least in principle.
Sorry, I was talking without the micro. Thank you, Ioannis. Any other question for Jeff? Don't be shy. We have the opportunity to ask him any other question. Okay, seeing none, I need to thank you again, Jeff, for this wonderful question. The recorded talk will be online, so we can see it again. And again, thank you very much and enjoy your stay here at our IAA and in Granada.
Thank you.